Okay, this is exciting. We've got a brand new unit and we're going to study, that makes no sense. Trimly iron a regretting Goth. Okay, new unit, and we're actually going to study what a coincidence. The exact same topic we did last unit. Now, if the previous unit seems kind of, I don't know, familiar, it's because if you had a teacher Jillian for geometry last year, sure enough, she went through the basics of the SOHCAHTOA, the sine, cosine, tangent. All of you actually had Jillian as your math teacher last year, but some of you had Jillian for geometry, and some of you had a statistics class with Jillian, but you all had Jillian last year. And so I didn't do too much change to that unit other than, hey, I think I'm going to refresh your memory. But as we got into that unit, I started realizing that some of you don't have some of the background skills that I assumed you had. And so we got to talk a little bit more now about, okay, showing step-by-step work and also understanding some of these algorithms and how they process. And so before we proceed and go deeper into trigonometry, I want to make sure we have some of the background, especially on how we communicate and demonstrate what we are doing, as opposed to just, hey, I push buttons on a calculator, or hey, they magically appeared. So how we found the answer, or why we know the answer is correct, is usually more important than, hey, did you get the correct answer? Do you understand the process? Right, and so what I want to try to do with this very first lesson, before we dive deeper into the trigonometry, is to try make sure we understand this. But usually in geometry, you would have learned some of the basics of the SOHCAHTOA, that the sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And then in Algebra 2, we normally go a little bit more in depth with the applications of trigonometry. And then either in Algebra 2 or in pre-calculus, we'll even start getting into some different identities and solving equations with the trigonometry. So we're kind of treading lightly. We maybe not getting quite as far in depth as I would have liked, but this. Okay, so let's go back to, I don't know, pre-algebra, possibly algebra, and play with some square roots, right? Before you ever got to algebra, you should have worked with a variety of numbers and fractions and square roots. And so let's review some square roots, right? If I have something like square root of 50, well, most of us can just eyeball and say, hey, I got to use 25 times 2, because the square root of 25 becomes plain old 5. Square root of 2, we're stuck with it. Square root of 63, again, this one's probably pretty straightforward. You're thinking, hey, how about 9 times 7? Because I can take the square root of 9 and get 3. Square root of 7, we're stuck with it. There's our answer. Don't be silly if you come across something like square root of 16. That's just plain old 4, right? Don't overcomplicate it. Also notice that I stopped, right? Square root of 16 is 4. Sometimes I'll see students do something silly, and they'll take the square root of 16 and they'll get 4, and they'll say, hey, I can also take the square root of 4, and then they write down 2. No. We just take the square root one time and then we stop. Square root of 21. Okay, so this is one of those ones where I start scratching my head because I'm thinking, well, all I can do is 3 times 7, but I can't take the square root of 3. I can't take the square root of 7. So I actually just need to leave it as the square root of 21, right? Sometimes I cannot simplify the expression, right? If I've got a prime number, it won't simplify. Or if all of the factors of the number are prime numbers, it won't simplify. Oh boy, now what if I start coming across something where maybe it's not quite so obvious which pair of numbers I should choose? So I'm going to do the square root of 72, and you can see that I've got it set up not once, not twice, but 3 times. Right? Because some students might say, hey, I want to try 9 times 8, because I know I can take the square root of 9. Problem is, square root of 8 also simplifies. Right? 8 is 4 times 2, and I can take the square root of 4. Finally, 3 times 2 makes 6, so I get 6 root 2. Now, maybe another student says, oh, 9 times 8, you crazy? I want to do 4 times 18. Now, truth be told, not too many of us are going to pick 4 times 18, but it could happen. Square root of 4 is just 2. But now I've got square root of 18. How does that simplify? Well, 18 is 9 times 2. Square root of 9, of course, is 3. And so now I've got 2 times 3, which is 6. And of course, I've got that square root of 2 that's just going to sit there and say, hey, I got the exact same answer. Right? Math isn't really fun until you find more than one way of arriving at the correct answer. Now, when the next student comes along and they say, hey, guys, 36 times 2, right? Think about it. 36 times 2 is 72. Square root of 36 is 6. I'm done. So what am I going to do if I don't magically come up with 36 times 2? Maybe memorizing the times table is not my thing. And obviously things like 4 times 18 would not be something you'd memorize. Same thing with 36 times 2. That's not something you'd have memorized. So if you don't just magically say, wow, 36 times 2 is what I need to do, here are 2 methods to maybe help you figure out. Okay, so because this is the direct route, right? 36 times 2. Well, one method is I could list all pairs of factors, and so I go in order. I'm thinking, okay, 1 times 72. Okay. Does 2 divide in there? And I might have to grab a calculator. 2 times 36. Does 3 divide in there? Again, I might have to grab a calculator. 72 divided by 3. Aha! 24. So 3 times 24. Does 4 work? And again, I might have to grab a calculator and try and check that. So, oh yeah, 4 times 18. Does 5 work? Well, 5 will divide into 72, but not evenly, right? I get like 14.4, and 14.4 is not a number I want to play with here, so 5 won't work. So then I go up to 6, and here's one you should have memorized from your multiplication table, 6 times 12, right? I'm hoping you've got up to 12 times 12 memorized. Does 7 divide in there evenly? No. Does 8? Yep, I get 8 times 9. And that will be the last one of the bunch, right? Because if I try the next one would be 9 times 8, and that's a repeat. So it's okay, so identify the perfect squares. Well, 1's a perfect square, but that really doesn't help me because I'd still have that 72, which is what I started with. 4 is a perfect square, and of course in one of the examples I did 4 times 18. 9 is a perfect square, and again, in one of the examples I did, 9 times 8. And 36 is a perfect square. So, those are my choices, and the best option is going to be the largest. So I would select the largest perfect square, which of course is 36, and so 36 times 2 would be my pair. Now, some of you are like, listing all the pairs is not going to be my preferred method. Well, if you're not into making a list of all the pairs, you could make a factor tree. Nice thing about factor trees is that they're going to look different from student to student. Pick anything you want for 72. And maybe you're thinking 6 times 12. Okay. What happens to that 6? Well, that's 2 times 3. That 12? Well, I could do 2 times 6. And finally, we've got a 6 still available, and that's 2 times 3. So there is our prime factorization. I've got a 2, a 3, a 2, a 2, and a 3. So I can pair up some 2's, right? I see a 2 times 2. I can pair up a 3, so I got 3 times 3. And then I can multiply those together and say, aha, 2 times 2 times 3 times 3, I get 36. And there was a leftover on that tree, right? There was a 2 left over. So that's what tells me I want to use 36 times 2. Okay, so again, let's revisit pre-algebra, or possibly algebra, although if you're learning this in algebra, you're kind of a little behind the schedule, right? This should have been a pre-algebra skill where you're manipulating fractions and square roots, right? Because you're doing these skills in isolation, you're not actually applying them algebraically. We do not like to leave square roots on the bottom of a fraction, right? It's a denominator is a fancy name there for bottom of a fraction. So what do? Well, we're allowed to add 0 and we're allowed to multiply by 1, right? If I add 0, I don't change the value. If I multiply by 1, I don't change the value. So I can multiply by the number 1, but I'm going to disguise the number 1 as square root of 2 over square root of 2. And of course, in the denominator, square root of 2 times square root of 2 makes square root of 4. Square root of 4 is plain old 2. 6 over 2. What can I do with 6 over 2? Well, 6 is really 2 times 3. And so I end up with 3 square root 2. Bum, bum, bum. Let's try another example. Again, we do not want to have a radical denominator. Fancy way of saying we don't want a square root on the bottom of the fraction. So I'm going to multiply by the number 1. Because if I multiply by the number 1, I do not change the value of the expression. You're also allowed to do that. We were going to disguise the number 1 as root 7 over root 7. Of course, square root of 7 times square root of 7 is the square root of 49. Square root of 49 is plain old 7. And try as I might, this won't reduce, right? 5 over 7, that doesn't reduce. So we're done. I still have a fraction. However, I don't have a square root in the denominator anymore. 3 divided by square root of 6. How does something like this work out? Okay, there's another example. Again, I can also multiply by the number 1 and not change the value. And I can disguise the number 1 as square root of 6 over square root of 6. And of course, square root of 6 times square root of 6 is square root of 36. Square root of 36 becomes plain old 6. You're maybe starting to kind of get in the hang of this. And you're saying, oh wow, look at that. When I had square root of 2 on the bottom, it turned into a plain old 2. When I had a square root of 7 on the bottom, it turned into a plain old 7. If I had a square root of 6 on the bottom, it turned into a plain old 6. And how does this happen? Well, look what's going on with the numerators up on top. Right? To make that square root of 6 become a plain old 6 on the bottom, I've got that square root of 6 appearing on top. Same thing happened with the previous example with that square root of 7. To make the square root of 7 on the bottom become a plain old 7 on the bottom, I've got a square root of 7 appearing on top. Now this will also reduce though, right? This third example does reduce because 6 is really 2 times 3. I can cancel out the 3's. And so I'm still left with the fraction, right? Of course, I now have a rational denominator. I should say I've got a whole number denominator, right? But it's definitely not a radical in the denominator. So we also want to make sure that we can simplify our square roots. And if in the process when we're simplifying, we come across with a square root in the denominator, we want to rewrite that. Okay, so missing value of right triangles. Again, we took a peek at this already in the previous unit. But some of you seem to want to like grab calculators and come up with some weird decimal answers. And we're like, no, 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 no. We do not want to grab a calculator and come up with weird decimal answers. First thing I want to do every single time is I want to write down a squared plus b squared equals c squared. Because sometimes I actually do end up adding, but sometimes I end up subtracting depending on what sides I know or don't know. Again, c has to be the hypotenuse. So square root of 29 has to be c. And of course, if I'm looking at the diagram, 3 is opposite angle A. So 3 can go in for A. If the angles were not labeled, the A and B are mix and match, but the C has to be the hypotenuse, right? There's never any discussion with that. But here, because I have the vertices labeled, I know that 3 has to be side A. Now, of course, if I've got square root of 29 and I square it, I just end up with a 29. Now, to undo the addition, I've got to subtract, right? 9 was being added to b squared. Opposite of addition is subtraction. I now know that b squared has to be 20. Got to take the square root. Now, normally in algebra, we would put a plus or minus in front of the square root symbol, but by definition in geometry, the side of each triangle has to be a positive number, so we don't need the plus or minus. Square root of 20 becomes square root of 4 times square root of 5. Square root of 4, I can simplify. There's my answer. Right? We always want to simplify our answers. Now, sometimes you really don't have any work to show. Right? What's k? Well, gee, k has to be half of 10, right? This is one of our special triangles. I know k has to be half of 10. Well, gee, that must be 5. M, well, again, on our special 30, 60, 90 triangle, m is just going to be k times root 3. So m has to be 5 times root 3. All right, there's really no work to show there. Sometimes, however, I've got to have work shown, right? If I want to find w and I want to find the value of t, I'm not going to just do this in my head automatically, right? I know if I want to go from that 21 to w, instead of multiplying by root 3, because the direction I'm going, I've got to divide by root 3. And so again, I'm like, okay, how do I simplify this? I multiply by the number 1, but I disguise the number 1 as root 3 over root 3. And of course, during this process, the square root of 3 in the denominator becomes a plain old 3 in the denominator. And when we accomplish that, we have our root 3 appear in the numerator. And of course, that 21 just kind of sits there until this last step where I say, hey, 21 is 7 times 3. I can cancel a 3 in the numerator with a 3 in the denominator. I get 7 root 3. So w would have to be 7 root 3. And I really need to show work to justify that answer so I can see where it came from. And of course for t, And I can show a little bit of work here. I'm saying, okay, I got to multiply w by 2, and I get 14 root 3. Okay, now, what I often saw last chapter was that students wanted to use the sine or cosine button with their calculator, or they wanted to do something interesting when it says write the answer as a fraction, right? If the directions request a fraction, I want to see a fraction. Now again, write down the Pythagorean theorem. The reason why I'll just write that down first is because when I first start out, I'm never quite sure if I want to do some adding or subtracting during the process. Aha, it looks like I really do want to add this time because I'm missing the hypotenuse. Now this would be a good place for a calculator. Most of us are not going to do 18 times 18 on paper. Most of us will not want to do 24 times 24 on paper. So this would certainly be a good time to grab a calculator. And then the same thing with the addition here. But I'm going to show each step on paper, right? Even if I'm grabbing a calculator to help out with the computation, I'm still showing each step on paper. Of course, I need to take the square root of 900. That becomes 30. Now, if I want sine of... Yeah, let's move that 30 over. Come on, 30, get over where you belong. If I want the sine of E and the cosine of E, right, I got to keep track of which angle I'm looking at. So I'm saying, okay, I'm looking at angle E. And because I'm at angle E, that affects the names of the legs. Right? Hypotenuse is not going to change, right? The hypotenuse is the largest side. It's across from that 90-degree angle. But because I am looking at angle E, the opposite leg is going to be 18. The adjacent leg is going to be 24. Right? Those names would trade places if I was looking at angle G instead of angle E. Now, SOHCAHTOA reminds me that sine is opposite over hypotenuse. So sine of angle E is going to be 18 over 30. That's opposite over hypotenuse. And of course, I can reduce that fraction to 3/5. But I'm just going to leave it as 3/5, right? If the directions say leave it as a fraction, leave it as a fraction. Back to SOHCAHTOA. The ka reminds me that cosine is adjacent over hypotenuse. So cosine has to be 24 over 30. Reduce the fraction. There are my answers, right? Sine of E is 3/5. Cosine of E, 4/5. This is my favorite type of question because there's no picture. Right? It says, hey, please find sine of A if you know that cosine of A is 15 over 17. Okay, so what do I do first? Better draw a picture. Right? If a picture is not provided, I better draw a picture. And what kind of picture? Well, it better be a right triangle. We use A, B, and C unless it's directed otherwise, where C will also be the right angle. I have to figure out, okay, now what angle am I focusing on? I'm focusing on angle A. Hypotenuse, of course, never changes. That's opposite the 90-degree angle. But the side opposite angle A has to be opposite. The other leg will become adjacent, right? The word adjacent means next to. Cosine is opposite over hypotenuse, right? SOHCAHTOA reminds me that, right? Cosine is opposite over hypotenuse. Cosine adjacent over hypotenuse. So if cosine is adjacent over hypotenuse, that 15 has to be adjacent, the 17 has to be hypotenuse. But if I'm trying to find sine of angle A, I want opposite over hypotenuse. And the opposite leg is, I don't know. So what do I do? Again, the first thing I'm going to write down is a squared plus b squared equals c squared. Right? Because sometimes we end up adding, sometimes we end up subtracting. But I want to write down the equation so I don't automatically just add. Because students get button happy on calculators. 15 times 15 is 225. 17 times 17, 289. And of course, this time I actually need to subtract. Right? I have the hypotenuse. I'm missing a leg, so I actually end up subtracting. Now, if you're thinking, whoa, 64 seems like that's way too big, that's because I haven't done the last step yet. I got to take the square root. I get 8. So now I know the opposite leg has a value of 8. SOHCAHTOA reminds me that sine has to be opposite over hypotenuse. So sine of angle A has to be 8 over 17. Right, so there shouldn't be anything really new this lesson. It's just that, hey, we've got to show work and we've got to simplify radicals. Right, so it's really, really, really drawing on a lot of your previous math abilities here. Most of which were required in pre-algebra and algebra for the computation. And then, of course, the SOHCAHTOA should have been acquired in geometry and then refreshed with our previous unit here in Algebra 2. Right? So I know this video was a little bit lengthy, but I have to really reinforce the need for showing work and how to show work. Hopefully you won't find the worksheet to be nearly so time-consuming as this video was.